And it worked. We did the data impact studies, and just, I don't want to say out of the box to minimize my effort and think that I wasn't, but it was really shocking.
But going forward, more data, okay? More data into data assimilation systems. And more data into data assimilation systems means your forecast models improve, whether they're AI models or whether they're traditional physical models.
In academia, we're really focused on not just the technology, but also the social science aspect as well. So,
similarly, nobody told us, hey, go build a radar, it's on our requirements. It wasn't, because nobody thought it was possible for another 2 decades or so.
There is a potential that we could find ourselves in a situation where going directly from the observations to forecasts or predictions of the things that we care about could bear fruit.
Great, thank you so much. Thanks everybody for being here. Really pleased to have you all, so thank you for participating. We got 40 minutes, a lot of questions and interesting topics to discuss. We'll have 2 questions, we'll do a quick round. I want to answer from each of you, and then I have one dedicated question for each of you. So we'll kick right in. The first question is, how do you see the intersection of commercial weather data and public institutions evolving to advance atmospheric science over the next 3 to 5 years? And we'll start with...
Sorry.
Go ahead. We'll actually start with Mitch.
hey, so during my introduction, you heard that I used to work at NOAA, but I used to work for NOAA for like 30-something years. So it's been a long, long time. And so I joined City College, New York, just a year and a half ago. So it's been a big transition. So just to be called professor, like I said, professor, and I go, who are you, who, is that me? And so it's a good question. And what I've learned recently, or over the last year and a half, that at academia, and I'm with an engineering school, and so we have really smart students and postdocs, and it's incredible what they can do. And you can tell with all this AI machine learning work, it's really being done by mostly young people, because they're really, we have to give them the guidance. The older people, I still listen to Bill. He's been around for a long time, and so it's you still need some guidance from older folks like myself, but you can talk to these postdocs and students and say, hey, this is the big picture, this is what we want to do, and it's amazing what they think of. And so we can really come up with outstanding solutions. I think over the next 3-4 years, it's still going to change over the next 3-4 years, this excitement of AI data-driven. I mean, I didn't even know what that meant 5 years ago, and now I do. And all these tools that are available, people are providing community tools. So, so I always think of AI machine learning, if you can imagine it, and you think of the data and think what's correlated, you can make it happen. So in terms of being in academia, it's amazing the talent, the freshness of the people thinking of new ways of doing things. Like, it's just incredible, the access to the talent pool. And I think that's true across all of academia. Just the talent's out there. And so it's going to be, and just providing exciting data, just to inspire the students when you talk about this and CubeSats and data, the high tempo refresh is so important. They really get excited by this data. And also when you tie it, like you did, the video is great. When you tie it to, not just doing retrievals or forecasts, but why it really matters to society, the impact-based activity. Social science is a big area. I mean, resilient communities, vulnerable communities, rich and poor, as mentioned, they really get that too. So in academia, we're really focused on not just the technology, but also the social science aspect as well. So it's very exciting. I mean, 5 years ago, I didn't even know what social science was, right? We didn't care. We just cared about if our retrieval error was improved by 0.3 of a degree. But knowing what it really means to society is really, really important these days. Thank you.
Thank you. Over to you, Marc.
So Marc Gasbarro, I've retired Air Force weather. joined NOAA about 3+ years ago, and now over at the NESDIS Commercial Data Program Office, where we focus on buying commercial data for space-based environmental monitoring purposes. And we have two lines of effort. One is purchases, operational purchases, which currently that's just the radio occultation with Spire, Global, and Planet IQ. But we also do pilots, and we've done multiple pilots. We piloted radio occultation back in the day in the late 2010s, started in 2016. Then we grew, moved that to operations. And we did a pilot for space weather, space ionospheric measurements using radio occultation. We're working to try to figure out what's next with that. I think we got some way forward. Did reflectometry with GNSS reflectometry measurements with Spire Global, but there's other companies like Muon Space that's rapidly catching up with that. And then now we've gone a whole different direction, and for the first time we're doing something that's not GNSS based, and that's microwave. So it's a whole different, we are the Commercial Data Program Office, not the Commercial RO Office. So now we have a new pilot that we've awarded to Tomorrow.io and Orbital Microsystems, so we're very happy to have them on board. For commercial data in general, the bottom line is this. For the next 3 to 5 years, and I'll even go beyond 5 if you don't mind me here, but commercial is growing. There's an insatiable appetite for data, more data, and you know, there is a growing need for perishable weather data, not just within the governments, but the international governments, WMO centers, private enterprise, you name it. Government satellite systems do an excellent, phenomenal job, but they're not enough. There's a lot of gaps in the network right now. You think of microwave, you have what's flying on our JPSS satellites, and then you have MEDOP. Phenomenal, resilient satellites that can last a lot longer than what commercial platforms can provide. So government satellites are more resilient, and they can provide more bespoke on-orbit options. However, there's a lot of gaps. So, and those government systems are a long lead to build, whereas commercial offers greater flexibility, much shortened acquisition timelines, rapid deployment, and the bottom line is they can provide a lot more data rapidly. So NOAA sees the a working relationship between commercial and government. One is not going to replace the other going forward. It's always going to be a supplement to the NOAA government backbone, but it's a viable and pertinent supplement.
Yeah, thanks. First of all, also a huge shout out to the video. I mean, I'm inspired after watching that. I feel like I want to go home and write some code, bring it to reality. Now, to get back to the question, and I'll just calibrate a little bit, I think with how rapidly we're seeing the field change, even asking me, what do I see as the future in 3 to 5 months might be a tough question to ask, right? Things have just changed so rapidly. But I will keep my answer a little bit short, and I'll double down on something that Marc said, that really the ability, sorry, I'll keep the mic a little bit closer. The ability of Tomorrow.io to get birds in the sky, you saw with the sounders, those went up in August, another set of launches in December. It was a couple weeks until the data was actually calibrated, science validated, and ready operationally in our systems, driving our weather forecasts, which are available to customers, right? We're a satellite or a software as a service company. We're trying to deliver predictions that do improve people's lives, their ability to act as businesses. And it's really remarkable to be able to get that information back from space that rapidly. When we see the future of being able to determine what kinds of observations are essential, we'll have the tools now, I think, through AI, ML. It'll become much more accessible to decide what types of observations are really going to help lock down a forecast. That can be done dynamically as well, and we can rapidly build and scale observing systems that support that kind of information. So I'll just stop with that. You can go ahead.
Great, which is a great segue actually to the next question, which is what excites you most about the technical possibilities that emerge when you combine advanced capabilities from space, like our microwave soundings, with AI and ML applications, and maybe actually start with you, Forrest, because you're working on that every day.
Yeah, and I guess I can quickly follow on what I was just saying. Like, when I am looking at the possibilities as well as the challenges, again, we really want to address our advances and address what we work on at Tomorrow from the scope of what are the existing problems? what are the challenges we want to resolve? Uncertainties in numerical weather prediction systems, complexities in data assimilation systems. How can the new advances in machine learning, AI technologies really help us address these kind of things? How do they link in with our sounder systems? So what I just mentioned on the ability to determine what kinds of observations are really going to help close gaps in predictability, I think we've got some wonderful opportunities there. Pass it.
Thank you. So AI machine learning. Well, let's put it this way. AI machine learning is absolutely necessary to fill, as you said in the video, the gaps, the global observing gaps. I mean, even if you have satellites up there, now take your microwave radars, for example, your active radars, they're going to see at a small swath, and that's vital. But we need a ground truth anchoring mechanism to AI models, and the more ground truth you have, the better your AI models are. So using microwave radar or microwave sounders, those are excellent examples to help provide those kind of ground truth to help anchor an AI model going forward. AI also can help out with help derive geophysical products more effectively and more efficiently. I know that there's a crater that you guys are working with NOAA. I realize we fund a very teeny piece of that with NESDIS STAR, but working on the AI machine learning a little bit. So it's exciting, but it is growing rapidly.
I have to read your question. The exciting part about AI machine learning is combining all types of data, microwave, infrared, and everything else. But we have to make sure that the machine learning is not overtrained. So that's really important. So you got to really understand the real information content. Like, for example, I was dabbling in some machine learning, and I noticed a lot of people put latitude, longitude into the machine learning because, you know, there's climatology background, that's a function of latitude, longitude. You can like cheat a little bit. I call it cheating machine learning. Like you can say, hey, if I know I'm over a desert and I know it's daytime, I can get information better on the skin temperature, but the satellite measurement doesn't even see that at all. And so then the machine learning is overtrained, and it won't work well for other seasons. However, it might not be that bad because people, at the end of the day, you want the best forecast as possible. So there's something called data-driven, right? We call it data-driven AI machine learning. So it might be something that where you have a continuous data flow, and you train it as, you know, with recent data, and you just build up the training, and you have a continuous training, so you don't have that problem. And so we really have to think about how to do the AI machine learning. I think it's very effective at combining information. Again, it's like using your imagination. You can imagine like geostationary imagery, for example, when you see these movie loops, right? There's no reason why your imagination shouldn't say, well, can I predict the next 2 hours of geostationary, because the information content. The same thing with all the Tomorrow I/O CubeSats and all this data. That's why it's called data-driven. It's not called data-sparse AI. It's data-driven, means I need the data. So data's king now, and the problem in the past was too much data, and most of the data wasn't being used. So with AI machine learning, you're going to suddenly revolutionize that. You're going to maximize the use of data, but we just have to be careful that we have the computer resources that allows us to almost continuously update the training, because we want the very best products. So, you know, if you have a seasonal, if you're looking over the desert and you know that desert's hot during the day, there's no reason why you can't use that information if it's going to be continuous updated training. So anyway, it's a lot out there, but still, we're going to have to rely on access to computer power, massive computer power, and storage and memory and everything else. And you know, there's a lot of possibilities, but a lot of testing and experimentation is needed.
I'll go off script here for a second, but a question I want to hear from all three of you on this topic of AI versus, you know, physics-driven models and the impact of data. Do you see, you know, we have those ranking done by ECMWF and JCSDA and others on the impact of various types of observations on model skill. Do you see those impact scores or ranking changing between physics and AI models? And do you see, maybe these drives are requirements different than what we thought we need because now the models respond to different observations differently.
Okay, I know we're at a microwave meeting, but if
It's
you
not a
look,
microwave
but
meeting.
no,
You can go
okay.
off.
So if you look at information content, pure information content, right? We know like hyperspectral infrared has more information content than microwave, right? However, you got to remember, but microwaves are useful. I like microwave because it's also great for nowcasting applications. You see rain bands and all that, so that's important too. But remember, rain band, where you have interesting weather and weather that's difficult to model, that data is not used in the model. They run away for it. I don't think they use any surface sensitive microwave radiances now in the model. Over infrared, they don't even look at tropospheric infrared data over land. It's amazing how much data is not being used. So I think the ranking will change because because with AI you're going to be able to maximize the use of the data. So absolutely.
Right? Mark?
So I'm probably not the expert to ask that question, but as a traditional meteorologist, physical models are going to be around. They're not going to be replaced. But I think it really depends on the time scale you're talking about. If you're talking about the next 5 to 7 days, it's going to be very difficult to replace physical models. And then there's AI models that are really rapidly growing and have already shown to outperform certain models beyond the 15-day time frame. So they think of your seasonal to sub-seasonal time range, say from 15 to 45 days. But right now, everything I've seen, and maybe I haven't been looking in the right spot, is physical models, AI models. I want to see a time where the two are fused together somehow. Where especially you go from a few days out to your seasonal, your sub-seasonal time frame, where you pretty much have to go all either more of your statistical approach or AI approach. There needs to be some kind of fusing with physics and AI and the not, I call it the medium term.
Yeah. Forrest, same question.
I'll answer that question with saying I cannot wait to actually answer that question through the data. I want to go and dig into it. I think we now have community tools that are going to help us answer those questions. And I would bet everybody in this audience is going to agree with me that the answer is going to be condition dependent, right? Those charts that we've seen have historically been full atmosphere, a couple of variables, and we kind of don't really understand how it necessarily applies to impacts or making decisions based on that information. So I cannot wait to use the new ability from toolkits that have been provided by Anemoy, NVIDIA, for example, to really dig into that problem and explore things like overall AIFS performs tremendously. Hurricane intensity, is that something where microwave sounders, the impact is extremely valuable versus some other observation system? And I think that's going to be a tremendous area to explore. I think that's also one of the areas where if we start to look at how the field winds up, where you have industry, public sector, private sector, academia, all working together, that's a huge opportunity for academia to be doing those kinds of observation-based physical process study, really probing and testing in the models and understanding why some of these things are the way they are. And that'll help us then design the experiments and the observation systems that then close the gaps to real-world problems.
Great. All right, we'll do one question each and then we'll open it to the audience. So start with you, Forrest. Can you walk us through how Tomorrow.io's approach to data simulation and AI-driven modeling is helping overcome traditional challenges in precipitation forecasting?
Yeah, so this is one that I alluded to a little bit earlier. How's my volume, by the way? I don't want to... Okay. So I alluded to this earlier, that we'd recently gotten our microwave sounders on orbit, and within 2 months, the data was calibrated, validated from science perspective, and being used operationally in our systems, specifically for precipitation retrievals globally and for precipitation nowcasting. And so that's a really nice example of being able to take the existing observation network, which is GOES, MRMS, the GPM instrumentation, other sounders, as well as our own instrumentation, and look at the problem of precipitation at global scales and think through, how does deep learning help us solve this, right? And so we got to the point where we have a network that can retain information from individual overpasses and be able to leverage that as forecasts of opportunity, basically. And I think that's a really good example for the way that we perhaps see the field continuing to grow, right? Precipitation at nowcast ranges is hopefully only the start. We really want to get to the point where we're seeing individual observations that have a large ability to make an impact on a forecast scenario, to really close the gaps in uncertainty. We want to have the mechanisms in place to be able to leverage that information in real time and do so.
Great. Mitch.
I want to say something off script a little bit. So you're the one that's doing the precipitation real time? Guilty. I can tell you it's really good. So at University of Maryland they have something called NPrecise. Yeah, NPrecise. And it's a validation system that brings all these satellite products of precipitation, compares it to, I guess, MRMS and things like that. And you're always the winner. And because I think yours is the only one that's actually AI driven model. And
We
it's really
didn't
good.
pay him to say that.
I know.
No,
I just, it's really good. Congratulations.
I have to clarify, and this goes with the thing, that the reason it's good is because of the quality of the observation. Right? The observation itself, the sounder, is tremendous. And the amount of work that was needed, right? We basically trained the system on the tropics data. And then it trained pretty well, it looked pretty good. But I was genuinely shocked that the first time we did the transfer learning and then turned it on, and Hurricane Milton had just come through on the heels of Helene. We'd gotten great science data, and it worked. We did the data impact studies, and just, I don't want to say out of the box to minimize my effort and think that I wasn't, but it was really shocking, and it just speaks to it's a testament to the quality of data that we received from the science team, from the space and sensors team. Shout out to Joe's crew, to the actual folks that you saw in the video launching things. I'm way over my time.
But going back, I'm just curious. So did it end up in NPrecise because of the crater that you had with NOAA? How did it get in there? Yeah, through the crater. Oh, good. Excellent. Good to hear.
All right, Mitch, you're reading up from your answer time. So give us a short answer on how do you see the role of academic institutions evolving in validating and leveraging commercial weather data for research? Which is kind of what you just
sort
discussed.
of like what I said in the beginning. Maybe I got confused with the question you asked. But no, the role is for us to be able to, we're very, we're an institution trying to learn and get better and understand different applications. So in terms of validation, we're curious. We have different methodologies to do validation. NPrecise is one. It's not from my institution. It's from University of Maryland. But we can have a large role in really focusing not just on the validation, but also, again, a lot of good engineers, a lot of good remote sensing scientists to understand the root causes. So it's not just the validation. It's really understanding why do we see these differences. And that's where we can be very, very, very helpful, because you guys might be busy doing other things, like you might not have the time to really do a deep dive analysis, and that's where we could help you out.
Great. Marc, from NOAA's perspective, what unique opportunities do you see in integrating commercial data streams into operational forecasting systems, particularly for high-impact weather events?
So I will sum this up in 2 words, and then I'll explain, of course, more data. You mentioned the word scalability. Commercial is a much better at scalability than the government does, for obvious reasons. So But going forward, more data. Okay, more data into data assimilation systems, and more data into data assimilation systems means your forecast models improve, whether they're AI models or whether they're traditional physical models, which I still believe both will coexist in the future. Okay, so we've seen already through our radio occultation contract and doing various OSSEs and OSCs and impact analyses studies that there is a huge boost in forecast accuracy. Okay, that would mean not just forecast accuracy, but decreased forecast error, increased forecast skill, decreased forecast uncertainty. So when you do like an ensemble of data analysis out in the future for X amount of days, shortening your uncertainty, and that means better decision making. So that is all viable and what we need going forward. So that's the bottom line. Is it all impacts numerical weather prediction?
Great. So with that, I'll just say I think this is my 8th AMS conference, and the two biggest trends we're discussing now, and I think this whole conference is about, private observations from space and other domains and AI, were really just PowerPoints 8 years ago, and we're now like, it's crazy what's going on, and the pace of change is rapid. So I can't wait to be here. I think it's Houston, Texas next year. Can't wait to be there and see what we're talking about and how fast things evolve until then. But until then, I really want to thank you all for participating and you all for listening and the engagement. And thank you very much.
Congratulations.